the key concepts in regard with the question number 1. We're going to touch on the key concepts, the theory part, and also we relate it to the map work part. So it's just a lecture to prepare you for the final examination when you're preparing for your question number 1 in paper 1, which is basically a question on climate and weather. Right. Without wasting time, we need to start with the background. We are going to look at the background, which is basically our grade 11 work. And this background is very important because it will help you to understand better the concepts that you're going to learn through the question of climate and weather. It's basically the background information, which is the basis of the understanding of the concepts under climate and weather. Right. So we are going to start with the high pressure cell and the low pressure cell. The difference between those two pressure cells. Right. And basically, we are going to differentiate between the two pressure cells in the southern hemisphere and in the northern hemisphere. Right. Because they are actually different according to the different hemispheres. Right. If we look at, we're looking at the first part here, we're looking at our high pressure cell. Our high pressure cell is actually what we call the anticyclone. The high pressure cell is what we refer to as the anticyclone. So it's basically an anticyclone, the high pressure cell. If we are to talk of it in another geographical perspective, we're talking of the high pressure cell as an anticyclone, like anticyclone like that. Right. And a low pressure cell, we are basically referring to it as a cyclonic cell. Right. So basically, when we're talking of cyclones, we're talking of low pressure cells. When we're talking of anticyclones, we're talking of high pressure cells. Right. We want to look at the difference between those two. Right. The first one is saying the air subsides. If you check at the bottom here, you see that the air is subsiding. Meaning to say, when we're having a high pressure cell, we have typically descending air. The air will be having a downward movement. If this is our ground, we are saying the air is coming from the upper atmosphere, is converging in the upper atmosphere. There's convergence here in the upper atmosphere, and the air is descending or is sinking. And as the air sinks, it's going to diverge in the lower atmosphere, which is our ground surface. So there's convergence in the upper atmosphere, and there's divergence at the bottom here. That is basically the high pressure cell. And it says the air diverges at the center. We've talked about that. The air is diverging here, is going into different directions. It sinks, it meets in the upper atmosphere, and it goes down. And as it goes down, it diverges in the lower atmosphere. We have clear or dry skies. That is typical of an anticyclone. When we're having anticyclonic conditions, we have clear conditions. We do have clear skies, or we have dry skies. Why do we have dry skies? It's because the air is sinking. For us to have unstable conditions, we need air which is uplifting. But in this instance, the air is actually going the opposite direction. The air is sinking, which will result in dry skies or clear skies, or what we call the stable conditions. Right. And there's also no release of latent heat and no cloud formation. Yes, we cannot have clouds forming. Clouds need to form when we have upliftment of air, of warm and moist air. Then the air circulates in an anti-clockwise rotation. Right. If you are looking at our high pressure cell in the southern hemisphere, the air moves out of the high pressure cell, not in a straight motion, but it circulates. And the circulation is anti-clockwise, like what you are seeing here. It's anti-clockwise against the direction of the clock. The clock, remember, is 12 there, and it's 6, and is 3, and is 9. The clock moves in this direction from 12 to 3 to 6 to 9. But if it's anti-clockwise, it means it's going against the direction of movement of the clock. So it's anti-clockwise rotation. So the air, as the air is actually coming out of the high pressure cell, as it diverges on the lower atmosphere, it diverges in an anti-clockwise circulation. Then we also have the isobar values increase towards the center of the high pressure. Right. If we check here, the center of the high will be the mid of our high pressure cell. Like if you can check here, you tend to find that this is actually the center of the high pressure cell. We're having the center here, which will mean that we have a higher value here. Like if you see what you are seeing, we have 1035 hectopascals and we have 1030, which means our isobar values are going to decrease as we go out of the cell. The highest figure should be at the center of the high pressure cell and they will decrease going outwards. And also you need to note the isobar interval, the difference in pressure between two next isobars next to each other. Like if you can check here, our isobar interval is 5 hectopascals. The first one at the mid of the high pressure cell is 1035, like this one that we are seeing here. And the next one is 1030, meaning to say our interval there is 5 hectopascals, which means the pressure is changing or is indicated in intervals of 5. Right. And you also, it's called anticyclones. We've talked about that. And we have typical 3 subtropical anticyclones that affect the weather system in South Africa. We have on the west, we have the South Atlantic, and we have on the east, the South Indian, and also we have over the interior, we have the Kalahari anticyclone or the Kalahari high pressure cell. Those are the 3 typical anticyclones that affect South African weather. So we basically have on the west, the South Atlantic, on the east, the South Indian, and over the interior, we do have the Kalahari high pressure cell or Kalahari anticyclone. Right, then we quickly go to the low pressure cells, which are the cyclonic conditions. Right, here is now basically the opposite. We have said that the high pressure cell is an anticyclone. Now the low pressure cell is a cyclone. It's a cyclonic system. And how does it operate? If you are to check on the low pressure cell, right, the low pressure cell, you can see that typically at the center of the cell, we have the lowest pressure occurring there. Like if you can check what we have at the mid of this system here, we have 1000 at the middle here, which is lower than what you are having on the outer part of the system. This is 1000, this is 1005, meaning to say our pressure is lowest at the center of the system, which is the opposite of what's happening here. The pressure was highest, the atmospheric pressure was highest at the center, but now it's lower and our isobars value are increasing as we go out of the system. As we move out of the center of the system, from the center of the system, our pressure is increasing. The atmospheric pressure is increasing as we go out of the system. So that is typically a low pressure cell. So we have air ascending. Ascending, we are saying we have air which is uplifting like this. The air now is acting opposite of the high pressure cell. There's convergence at the bottom, assuming this is our ground. The air comes from high pressure and it converges. As it converges, it rises. And as it rises, it diverges in upper atmosphere. So there's divergence there in the upper atmosphere and there's convergence at the bottom. So that is basically the difference. And given this condition, we are most likely to have unstable conditions. We have cloud formation. Like if you are saying this is warm and moist air, which is converging and which is ultimately being forced to rise, it will ultimately get to the dew point level. It will condense, it will create clouds that are going to produce rainfall. So typically we have unstable conditions when we have a low pressure cell. It creates unstable condition. Condensation will take place because of the upliftment of the air. The air now is going upwards, is going into upper atmosphere, is going to reach at the dew point level, is going to condense and is going to form clouds that will apparently bring precipitation. That is basically with a low pressure cell. And then latent heat is released during condensation. We have the release of latent heat, yes, as the condensation takes place, right? And also clouds form and precipitation occur. We talked about that. Then circular shaped isobars. Yes, they are circular shaped. You can see in this instance, the isobars are circular shaped. And we also have the air circulating now is a clockwise rotation. Take note of this. It's clockwise. When you are having an clockwise, but when you are having a low pressure cell, we have a clockwise rotation. So that is basically the difference of a high pressure cell and a low pressure cell. The circulation out of the high pressure cell is anti-clockwise, but the circulation into the low pressure cell as the air is feeding into the center of the low, it will be circulating in a clockwise direction. We are talking of typical of the southern hemisphere in this instance, because the circulation is not the same. It's the opposite in the two different hemispheres. If you are to look at the northern hemisphere, the circulation into the low is anti-clockwise. Circulation of air into the low pressure cell in the northern hemisphere is anti-clockwise. It's the opposite of what happens in the southern hemisphere. But basically for our studies, we are more focused on our southern hemisphere, since our questions are typically related to our typical climatic conditions in the south. So the circulation into the low pressure cell is basically a clockwise rotation. Then it's also known as a cyclone. We've talked about that. Isobar value decrease towards the center. We've talked about that. Then which typical low pressure cells do we have geographically? We have the coastal low. The coastal low, when we're talking of the coast, we are looking at the boundary of the waterboard and land. Coastal areas are those areas that are bound to the sea, those harbor places. Like you can talk of Devon, you can talk of Port Elizabeth, you can talk of those places which are just by the seaside. So we do have a typical low pressure which exists along those typical lines along the boundary of land and water. That is basically what we call the coastal low. And we are going to look at them when we do the backquins. When we're looking at the backquins, we are going to have a look at the coastal lows, because they are the ones that influence the occurrence of the backwinds. Right. Then we also have what we call the mid-latitude cyclones. Is typical of the first part of our study in climate and weather, which is also a question that you should take note of. Is a typical weather system that exists and that affects mainly the western part of South Africa, the western coast of South Africa, typically in winter, bringing in heavy rainfall and very cold conditions over the Western Cape in around Cape Town. The mid-latitude cyclone, we're going to talk of it. Then we also have the tropical cyclones, typical of weather systems that do affect the Southern African subcontinent, affecting mainly Madagascar, affecting Mozambique, affecting Zimbabwe into South Africa. Yes, it's typical of a weather system which is prevalent in late summer. We're going to look at it as we focus on it as a particular aspect of the study of climate. Right. So basically, we are looking at these concepts as background information. We need this background because it is going to be very useful, and we're going to use it as we go through the study of climate and weather. This is basically the background, and this is grade 11 work. You must be having this, and you must have it at your disposal of the fingertips. You must be knowing these things because they will apparently be very useful in your study of weather and climate as a particular topic, or also as a question in paper 1, question number 1. You must be very aware of the basic concepts of climate and weather. Then we also have to look at maybe the pressure belts. On the pressure belts, we don't need to waste much time. We just want to go through them, and they will also help us understand the formation of mid-latitude cyclones, and they will also help us understand tropical cyclones, because they are the basics of the study of those typical weather systems of the mid-latitude cyclone and also of the tropical cyclones. Right, we're now looking at our pressure belts. We are going to look at the pressure belts as fast as is possible. Right, if we check here, this is the polar region at 90 degrees south, and this is the polar region at 90 degrees north. We do have high pressure cells there. There is descending air, like what we have talked previously. When we have typical descending air, we do have a high pressure cell forming or an anticyclone forming. So at 90 degrees south, we have a high pressure cell, and at 90 degrees north, also you have a high pressure cell. There is descending air in those regions. Right. Then we go to the subpolar region, which is around 60 degrees to the north and around 60 to the south. In that pressure belt, we have a low pressure. That is typical of a belt which has got low pressure. It's called the subpolar low pressure belt. Right. Then we move on to the next pressure belt, which is around the region of 30 to the north and around the region of 30 degrees to the south. That is what we call the subtropical high pressure belt. It's subtropical high pressure in the north and subtropical high in the south. And South Africa actually falls within the subtropical high pressure south. It's dominantly in the subtropical high pressure south. Like if you check the latitude of South Africa, we do have latitudes ranging from around 23 degrees and 23.5 in Limpopo, the Capricorn. And as we go down, we do have around 30, 34 going down to Cape Town, which means South Africa is basically falling around this subtropical high pressure belt. Right. And we have the equatorial low, which we call the ITCZ, the Intertropical Convergence Zone. This is typical of the mid position of our latitude values at 0 degrees. It is starting from 0, increasing, going to the north to 90, from 0 to 90, going to the north, and from 0 to 90, going to the south. And the central position is the equatorial low, which is at 0 degrees. And that belt is typically a low pressure belt. Because of intense heating, we have the sun being overhead across the whole year, and typically we have a low pressure cell developing because of intense heating. The air is always uplifting, there's convergence and there's upliftment, or the air will be ascending in that particular belt, and it will create unstable conditions and very high amounts of rainfall or precipitation in that particular belt. So those are the pressure belts that we have. So if you are to summarize it, start from the equator, start from the ITCZ, it's low, then it changes to high, it goes to low, and it goes to high. That's the sequence going to the north, and the same sequence applies as you go to the south. It's low at the equator, it's high at the subtropical, and it's low at the subpolar, and it's high as you go to the polar south. That is the sequence of the pressure belts. Then we go to circulation cells. And also the main problem that we usually have is learners that confuse between a pressure belt and a circulation cell. Those two are not the same. We do have 4 distinct pressure belts. The low pressure equatorial, the high pressure subtropical, the low pressure subpolar, and the high pressure polar. Those are the pressure belts that we have. Typically, we have 3 pressure belts. So if you get a question which asks about pressure belts, indicate the position and indicate the nature of the pressure. It's equatorial, meaning to say it's occurring around the equator. And what kind of pressure is it? It's a low pressure. So it's equatorial low. Then if you go to the next pressure belt, it's subtropical. And what kind of pressure is it? It's high. So it's subtropical high pressure. Then you go to the next belt. It's within the subpolar. It's not in the polar, it's the sub at 60 degrees to the north and to the south. It's subpolar high. So when you are naming those pressure belts, you have to indicate the location and you have to indicate the nature of the pressure in the belt. Do not just say it's polar. Do not just say subpolar or it's polar or subtropical. Then what kind of pressure is there? It's subtropical high, it's equatorial low, it's subpolar low, it's polar high. That is a complete description of a pressure belt. Then now let's quickly go through the circulation cells. Because of these pressure systems, we are going to look at the effect of Coriolis force as we go through the discussion. But for now, we just want to focus on maybe pressure gradient and look at the circulation cells. Because of the existence of differences in pressure between two pressure belts, if we have a high pressure cell and we have a low pressure cell, it will definitely mean that geographically there's pressure gradient. There is a difference in the levels of pressure, which will prompt the air to move from one region going to the other, because now there's a gradient. There is a difference in the pressure. Whenever we have a high pressure region and we have a low pressure somewhere, it will mean that the air has to blow from the high pressure going towards a region with lower concentration of air, which will be a lower pressure region. So because of that, it will create a sequence or a circulation that is going to exist. And it is going to create for us three typical circulation cells. Right. If we check here, we have a circulation cell which is happening here. The air is coming from the polar high, is going to the subpolar low, and is ascending, is feeding back, is going in that direction towards the closer to the Earth's surface. And as it gets there, the low subpolar, it rises and it feeds back to the high pressure cell. So at the end, it creates what we call a circulation cell. So typically we are saying there is circulation which is happening between the polar high and the subpolar low. Then if you also check here, there is another circulation happening. There is high pressure in the subtropical region here, if you can see, which means the air has to come from high going towards low subpolar, and is going to converge to meet with air coming from the polar high at the subpolar low region, and is going to ascend. Like we said, when there's convergence, the air is going to uplift, which will result in another circulation cell developing, like what you are seeing here. There is another circulation cell which is going to develop. And as we also check here, we also have another circulation cell which is occurring between the polar, between the subtropical high and the equatorial low. Because there's low pressure here, the air has to come from high pressure subtropical here. There is high pressure. The air is going to flow from high going to low, and is going again to converge from the air coming from subtropical south going to the equatorial low. It's going to meet there, converge, and also uplift and create another circulation cell. This is the circulation cell, and we also have another circulation cell happening there. So we are looking at those three circulation cells which do exist as a result of the differences in pressure along the different climatic regions and different pressure belts. So naming those cells, this is basically the same. If you have a question which is asking on the circulation cells, be aware of the three circulation cells that we have noted there, because it's basically the same. They might transpose them differently. This is on a globe like our Earth. You know, the shape of our Earth is spherical, and they might transpose them to a flat landscape. You have not to, I don't need to confuse yourself with that. It's still the same. We are just taking a perspective of the flat landscape, like what is happening here. What you are seeing here, these three circulation cells are the same cells that we have been talking about on the globe. So the North Pole, you can see that is indicated that is North Pole here, meaning to say we have 90 degrees to the north here, and we have our 60 degrees to the north and 30 degrees, and we have our equator, which will mean that this is 0 degrees, this is subtropical high, this is subpolar low, and this is polar high, though on a flat landscape. But basically, it's the same thing. So the circulation cell that we have from the equator, between the equator and the subtropical high, is called a Hadley cell. This one here is a Hadley cell. The first circulation cell, which is created by the circulation from the equator, from the subtropical high to the equator, the A rises as it reaches the equator, or the ITCZ. It converges, it rises, it creates unstable conditions over the equator, and it sinks back in the subtropical region, which creates a high pressure around 30 degrees to the north and to the south. Then again, we have another circulation cell between the subtropical high and the subpolar low. Because there is pressure gradient, there is high pressure in the subtropical high and there is low pressure in the subpolar low, we have air moving in that particular direction, and it's going to converge with air coming from the polar high. And it's going to create another circulation cell, which we call the Ferrel cell. It's cell number 2. It's hardly from the equator to 30, subtropical high, north and south. Then from subtropical high, that is 30 degrees, around 30 degrees to the north and to the south, we go to 60, which is the subpolar. We have a Ferrel cell. Then lastly, between the polar region and the subpolar region, we do have what we call the polar cell, like what you are seeing here. It's called the polar cell. So those are the three basic circulation cells that are created because of the existence or the prevalence of the different pressure belts on a global scale, or because of the distribution of the different pressure cells on a global scale. So we do have those three circulation cells. So when we get a question which is asking about the circulation cells, do not confuse circulation cell to pressure belt. Pressure is either high or low. And where is it? Mention the region and indicate the nature of the pressure. That is a pressure belt. Circulation cells, there are basically three. We have the three basic circulation cells, which is the Hadley cell, the Ferrel cell, and the polar cell. Right. Then we'll go to Coriolis effect. We need also to encompass Coriolis effect. It's very critical and we need to understand it, and it is going to help us understand when we discuss the weather systems like the mid-latitude cyclones and also the tropical cyclones. Right. Coriolis force, this is the force which is created by the rotation of the Earth. Remember, the Earth is not stationary. The Earth is rotating. It's giving us days and nights. And is giving us cycles of seasons and years because it's rotating. We have rotation and revolution. I think that is basic knowledge. You must be having that. We have rotation and revolution, which means the Earth is not stationary, it's also moving. So we are saying the air is moving from high pressure to low pressure because of pressure gradient. But however, the air is not going to move, or is not going to move according to our assumption of pressure gradient. Right, what am I saying here? We have if you have a high pressure cell here, there is high pressure around this region and there is low pressure there. It means there is pressure gradient between these two cells. There is a difference in pressure, which will definitely make the air flow from high going to low. It must attain a natural balance between those two pressure cells. There is high concentration of air molecules here, and there's low concentration here, which will prompt the air to move from the high to go to the lower. But however, there is also an effect of the rotation of the Earth. The Earth is also rotating, which will mean that the air, instead of it going straight from high to low, it has to be twisted in a direction because of the Earth, which is also moving. We are having a body of air which is moving over a moving body. So at the end, we do have a deflection, which we call the Coriolis effect. It will cause a deflection. Like the air will not move as according to pressure gradient like this, straight from high to low. It will not feed straight to the low, but however, it's going to be twisted in a given direction because of Coriolis effect. And this effect now, we need to note it clearly, how it affects the air in the south and how it affects the air in the north. And also, it is going to lead us to understand the planetary winds, what we call the planetary winds. For us to understand that they are based on Coriolis effect. Right. The deflection is to the left in the southern hemisphere. The air is going to be twisted to the left direction in the southern hemisphere, and the deflection in the northern hemisphere is to the right. You must note this. It's right in the northern hemisphere and it's left on the southern hemisphere. Let's go back to our illustration and see how that deflection will lead us to having different setup of planetary winds on a global scale. Right. We'll quickly go through our illustration of the globe, and we want to summarize the planetary winds that we have on a global scale as on the world Earth. Right. We have basically three different planetary sets of winds on a global scale. Right. Let's go to our illustration. Because we said deflection is to the left in the southern hemisphere and to the right in the northern hemisphere, which will mean that I will use this illustration here to indicate the deflective direction and also to indicate the nature of the planetary winds that we tend to happen in a different, in a particular geographical region. Right. We are saying here, we do have this belt. It's a high pressure belt. This is the polar high, around 90 degrees to the south. This is high pressure. And this is the subpolar. It's a low pressure. And this is a subtropical. It's a high pressure. And this one is a equatorial, or the ITCZ, which is the low pressure. The same sequence applies as we go to the north. It's low from the equator. It gets to high pressure in the subtropical. It goes to low pressure. It goes to high pressure at the end. So because of this, we tend to have air moving from high going to low. And also coming from high, it must go to low. Come from high, must go to low. From high, must go to low. But we are saying there is an effect of deflection, which is caused by Coriolis, which will tend to bend the air in a particular direction because of the rotational effect of the Earth. And we said our rotation is to the left in the southern hemisphere, which will imply that instead of this air going straight to low here, it is going to bend in that direction, leftwards. It's coming from high, going to low, but it's not going straight. It has to bend in that particular direction because of Coriolis effect. Then this one is coming from high, going to low, because there's Coriolis effect is also going to twist in that direction. And this is leftward movement. Do not confuse yourself, because these two air masses are seeming like going to different directions. They are still going to the left. They are still deflecting to the left. It's left going that direction if you're coming from south to the north. And if you're coming from the north to the south, it's still left again. Your left direction is not the same if you are moving from different orientations. If you're coming from the south going to the north, your left is on the other side. If you're coming from the north going to the south, your left is on the other side, which will mean that this is leftward deflection and this is also leftward deflection. And lastly, there is high pressure at the polar region here, and there is subpolar low, which means the air must move from high polar to the subpolar low and is also forced to deflect to the left. So this is going to create a belt of winds which has got this particular name according to the direction of flow of the air. Right. Geographically, let's go back. Geographically, we name winds according to their direction of flow. We name winds according to where they are coming from. That is how we name winds geographically. If we look at our indicator of wind direction, the wind vane, it points towards the direction of where the wind is coming from. So geographically, we also name winds according to the direction from which the winds are coming from. So if we check on our globe, this is the western part of our globe, and this is the eastern part of our globe. Remember, it's always west to the left and east to the right. And if we check these winds, they are starting from the eastern direction, they are going to the west. And where are they coming from? They're coming from the polar region here, and they are going in that direction. So this belt here is the belt of what we call the polar easterlies. They're coming from the east and they're originating from the polar region. They're called the polar easterlies. That is the belt of the polar easterlies. Then between this belt and this belt here, we are seeing that the winds are going in that direction. They are coming from the west going to the east. This belt is the belt of what we call the westerlies. And in this belt here, they are going in that direction. You can see they are coming from the east and they're going to the west. This is a belt of the winds which we call the trade winds or the tropical easterlies. It's tropical easterlies. They're coming from the east going to the west, and they are in the tropical region, or we call them the trade winds. Those are our typical planetary winds on a global scale. So basically, that is the basis of the understanding of the weather systems and the climate and the weather are part of paper 1 question number 1. So relating it to practical geography, which is map work, when you get typical questions asking about South African weather conditions, you must know that South Africa geographically is situated within the range of the subtropical high. That is why we have a limited amount of precipitation, because we are typically having stronger descending air. We are in a subtropical high pressure belt. So you need to actually figure out and relate to the belt in which South Africa lies geographically. South Africa typically lies within the subtropical belt. That is why we do not have as much rainfall, and also the rainfall is seasonal, typically because of the location of the basic location of the country according to the distribution of pressure cells. Right, let's quickly go to mid-latitude cyclones. That is the first part of climate and weather, the first part of the question number 1. You are typically going to get questions on mid-latitude cyclones. Right, I'll quickly go through the basics of mid-latitude cyclones. We don't want to spend much time. We want to look at, we talked about cyclones. We said cyclones are basically low pressure weather systems. So when we're talking of mid-latitude cyclones, we already have an idea of what kind of weather systems are they. They are typical of low pressure weather systems. But where are they prevalent? In the mid-latitude. What is the latitude range of values? We have our latitudinal values stretching from 0 degrees at the equator, and they will end at 90 degrees in the north, and they will also end at 90 degrees in the south. So where is the mid position of the range of values of 0 degrees to 90 degrees? The mid position we are saying is around somewhere 45, 50. So we are looking at typical low pressure weather systems that do exist around the mid values of our distribution of the latitudinal values from 0 to 90. So if you can check on the globe here, we do have the mid-latitude region. This is our equator, and we do have the mid-latitude region indicated in the south and also indicated in the north. And what you should also note is we also have other namings of the same weather system. Usually that is a typical question that you can get in the examination. Give another name for the mid-latitude cyclone. Typically, that is a common name that we use for the weather system. We call them mid-latitude cyclones, but you might get a question which requires you to identify another name for the same weather system. They are also called moderate cyclone, or they are also called extratropical cyclone, or they are also called temperate cyclones, or frontal depressions. These are typical names of the same weather system. So if you find a question which requires you to give another name or an alternative name for a mid-latitude cyclone, always remember that they are having other names like the moderate cyclone, the extratropical, the temperate, or the frontal depression. Those are other alternative names for the same weather system, the mid-latitude cyclone. Right, let's go to the developmental stages. We can also get a question which requires you to identify a developmental stage of the weather system. This system, it goes through a number of developmental stages, which are basically 4 stages. Right. We have the initial stage, the first formative stage of the weather system. Right. What you should note here is that this weather system occurs around or along the polar front. And if you're talking of a front, I am sure geographically, we know what a front is. A front basically is a boundary which splits two air masses of different characteristics. What are the characteristics that we're talking about? Air masses can be different in terms of temperature. One might be cold, the other one might be warm. Those two air masses, they cannot mix. They will be split. There will be a boundary which is going to develop between them because of their differences in the properties. One is cold, one is warm. Those are two different characteristics. So those two air masses cannot effectively mix. Then they can also be different in terms of stability. One is sinking, it's creating stable conditions. One is rising, it's creating unstable conditions. So they cannot mix. Or they can also be different in terms of their moisture content. One can be dry and the other one can be moist. Those two air masses are different. So they will be split. There will be a boundary which will exist between them. That is what we call a front. So typically, if we check on a global scale, we have the boundary which exists along the polar region, which will split the warm air, which is coming from the subtropical high, feeding into the subpolar low, and the cold air, which is coming from the polar region, feeding into the subpolar low. Those two air masses will be different in terms of their properties. One is coming from a cold region. The polar easterly is very cold. It's coming from a polar region and it's very cold. These are the westerlies. They are relatively warmer. They're coming from a region of higher temperature. So those two air masses will be split along the polar front in the subpolar low pressure belt, like what we have been indicating in the previous indication or discussion. So this is our polar front. This one, it's stationary and it's permanent, it's stable. It is a fixed boundary which is splitting those two air masses. So the warm air is going in that direction and the cold air is going in that direction. They are squeezing past each other along a stationary polar front. That is the first stage. Then, remember, there will be friction happening there on the boundary. The two air masses are squeezing past each other in different directions. They are ultimately going to cause a disturbance on the polar front. And the polar front is going to wave, which will lead us to stage number 2. If you now see here, this boundary is no longer straight like what it was in the first stage. is now waving or is now bending. And because of the bending of the boundary, the two air masses are now starting to circulate. The cold air is going to advance towards the warm air. And the warm air will also start to advance towards cold air, creating a circulation. That is stage number 2, which is the development stage, or what we call the wave stage. Then we go to number 3. You are seeing the difference here. This is a zone which is occupied by warm air. It's still wide when we have that disturbance on the polar front. But if you check here, the area which is occupied by the warm air is increasingly getting narrower and narrower. We have reached maturity of the weather system. The system is now strongly circulating and is now causing a displacement of warm air from the ground surface. The warm air is gradually losing its space over the ground surface, is being forced to uplift, and is now leaving the Earth's surface because of the advancement of the cold front. What we call the cold front on this side, we are saying is cold air approaching, cold air moving into a region of warm air. Then the warm front is this part here, where we have warm air advancing towards cold air. But however, there is a difference in the movement of those fronts. A cold front is much effective or is more faster compared to a warm front because cold air is denser and has got potential to push towards warm air, while its warm air is less dense and has got less potential to push towards a region of cold air, which will effectively mean that the warm sector is gradually going to get narrower and narrower because there's more cold air advancing than warm air advancing towards cold air. So this front will move faster going in that direction, the cold front. And this one will move very slow going towards this region of cold air. So ultimately, it means this space is going to get finished because the cold air will be moving faster compared to the warm air moving in that direction. So they are not able to maintain the same space because of the differences in the movement of the cold front and the warm front. So basically, that is the mature stage when the warm front has, when the warm sector is narrowed. Then we will go to occlusion. If we check here, stage number 4, you can see when we reach occlusion, we are saying there is a section where warm air has been completely displaced from the Earth's surface. We no longer have incidence of the existence of warm air over the Earth's surface. The warm air has been completely displaced from the Earth's surface. That is what we call the occlusion stage. So how do we show the occlusion on the weather system? If you check here, this indication here, I think you can see the differences in indications, right? This is a front, and if you see this triangular inclination, this is a cold front. And if you also check, if you see this semicircular, this is a warm front. This is a cold front. So when we have incidences of, it's the same front, there is cold, there is warm. There is cold, there is warm. This is what we call occlusion. What is the meaning of occlusion? We are saying the warm air has been completely displaced from the Earth's surface. It's now only occupying the upper atmosphere. The warm air has been displaced because of the fast movement of the cold front towards the warm sector, and it is forcing the warm air to be vertically displaced and is now only in the upper atmosphere. That is basically what we refer to as the occlusion stage, what we call the occluded stage. It will mean that the warm air has been displaced from the ground surface. We no longer have warm air close to the ground surface, but all the warm air is now in the upper atmosphere, or it has now gone to dew point and has created clouds, bringing in precipitation in different forms. Right. That is the basics of our mid-latitude cyclone. Then the other thing that I also want to focus on is the two types of occlusion. There is what we call a cold front occlusion. Then we have what we call a warm occluded front. Right. If you check here, When you get a typical question, like for those ones who wrote the Gauteng preliminary paper, there was a question which was asking you to figure out the nature of occlusion on a given question. If you check on the website, you also see I typically discussed about that particular aspect of the occlusion. Right. There is what we call a warm front and a cold occluded front, and also what we call a warm occluded front. Right. The difference here is when you want to note the difference between those two fronts, check the front which is touching the ground surface. Like, what am I saying? I'm saying if we have an occlusion like this is a cross section, when you're drawing a cross section, if the question asks you to draw a cross section, remember, you just have to draw the fronts and label them. Do not put the indications. We can only use those indications of a triangle and a semicircle. We use them on an aerial view, but not on a cross section. When you're drawing a cross section, you just draw your line. We know this is a cold front. And when we have another front here, this is a warm front. A warm front is gentle, a cold front is steep. And this, if this is our ground, we are saying it's the cold front which is touching the ground here. We know this is the cold front, and this is the warm front. And the cold front is the one touching the ground, which will imply that this is a cold front occlusion. It's a cold front occlusion. It's the cold front which is touching the ground. And what is the implication here? We are saying the air which is here is very cold. And the air which is here is cooler. So we do have very cold and cool air. So typically we are saying very cold air has got potential to advance towards cooler air because of its density. It's more denser if we have very cold air on this side of the front and we have cooler air on the other side, which will mean that this front will effectively move in that direction and the warm air will be displaced vertically. So this is basically the warm sector because there's very cold air on that particular side and there's cooler air on the other side, which will mean that very cold air is going to effectively push towards the direction of a cooler air and is going to effectively push the weather system in that particular direction. Then what we call a warm front occlusion, what you can also note, like for example, that Gauteng question, there was no indication of the front here to show that which front is touching the ground. So what were you supposed to figure out was check the nature of the air on the west part of the system and check the nature of the air on the eastern part of the weather system. Also remember that the weather system is always moving in that particular direction. It will come from the west direction going to the east. So if you see very cold air on the western part, it is meaning that it is a cold front occlusion because we have very cold air which is pushing towards cooler air on the east because the weather system will be moving from the west going to the east. That is a typical mid-latitude or a temperate cyclone. And what we call a warm front occlusion, we have this situation. The cold front is here. The warm front is there. The cold front intercepts here and the ground is there. I think you can see the difference there. If this is our ground surface and we do have the warm front being over the cold front, it is implying that this is the ground. It's implying that this is a warm front occlusion. And it is the warm front which is touching the ground. If you are checking here, the warm front is this one, which is gentle, is touching the ground. And the implication also is the same. It means we have very cold air here and we have cooler air on the side. What you should note is when you are indicating the two air masses, show that they are different in terms of their temperature. If you are using cold and cool, it's fine. It shows that there is a difference in temperature. Cooler air has got relatively higher temperature compared to cold air. Or if you want to use very cold and cold, it shows a difference. Very cold, it means the temperature is very low, is relatively lower, and cool air has got slightly lower temperature. So the indication is you must take note of how you indicate the different air masses. Show that one is more colder than the other. So you cannot say it's a cool sector, it's a cold sector or a cold sector on either side because there is no distinction there in terms of the relative temperature. But if you say very cold and cold, it shows a difference. Or if you say very cold and cool, it shows a difference. So you must show that the air masses do not have the same temperature properties. They are different, though they are both in the cold sector, but the coolness is not the same. One is slightly colder than the other. If one is minus 2 degrees Celsius and the other one is 0 degrees Celsius, those two air masses are not the same. Minus 2 degrees Celsius is very cold compared to 0 degrees Celsius. If one is 5 degrees Celsius and the other one is 2, they're not the same. They are both cold, but show the extent of coldness in terms of indication of the relative coolness of the temperature. So basically that is with mid-latitude cyclones. So typical questions that you can get of a mid-latitude cyclones if you are preparing for the exams, check on the developmental stages and check on the implications of the weather system over the natural environment, over the built environment, over human activities, over economic activities. How do they affect those different aspects of life? Right. So what you need to note is you need to note that the mid-latitude cyclones, they do affect South Africa, typically in winter, and they do affect the Western Cape. That is the region which is vulnerable to that particular weather system. And you should note that their movement is they move from the west going to the east. That is why they tend to affect the Western Cape because they will be coming from the extreme west over the Atlantic Ocean, moving over to the interior. Then you note their implications. How do they affect human activities? How do they affect the environment? How do they affect the economy? And also, you should note the strategies that we can put in place to minimize the negative implications or the negative impact of such weather systems. That is what you must be prepared for. And also, typical exam questions, you must be specific. If the question is also specific, do not generalize. If the question is asking on the impact of the mid-latitude cyclones on the environment, make sure you address the environmental impacts. Do not go to other aspects which are not environmental. If the question is asking about the economy, look at the impact of the weather system on the economy of the country. Be specific if the question is also specific. And remember, if it's a paragraph question, you must give a factor and a qualifier. What are we saying? Give a direct response to the question and qualify the response. Give evidence to support or to substantiate the factor that you have given. That is a factor and qualifier. For example, the question is saying, give the effects of mid-latitude cyclones on maybe the environment. Give an impact. They will cause extreme cold conditions. It's a factor. And qualify the factor. What are the extreme cold conditions going to pose on the environment? You are now qualifying the factor. So when you are answering paragraph questions or when you are answering the 2x2 questions, you must ensure that your point is fully substantiated. It's got supporting evidence Give a direct response to the question and qualify the response by adding additional support information to what you have highlighted. That is a factor and a qualifier. That is typical of what you should do when you're answering your questions. Right. We are done with our mid-latitude cyclones. We move on to tropical cyclones. When we're looking at tropical cyclones, remember we looked at the tropical region, which is the equatorial region. We are looking at low pressure weather systems that do occur or that do happen within the tropical region. Where is our tropical region? Basically, we are saying in the tropics, we have the Tropic of Cancer, which is at 23.5 degrees to the north. And we have the Tropic of Capricorn, which typically crosses through South Africa in Limpopo, Capricorn district. It's at 23.5 degrees to the south. So we are saying the tropical region typically lies within the belt of 30 to the south and 30 to the north around the equator. So we have typical low pressure weather systems that develop in that particular region. Those are typical of what we call the tropical cyclones. Right. We want to look at them in as brief as is possible. What makes those weather systems prevail? What are the basic conditions that will favor the development of tropical cyclones? And also, maybe before we look at that, you must also note that tropical cyclones are the most destructive weather phenomenon on a global scale. They are the ones that cause the most destruction or the most loss of lives caused by such typical weather system, because they are very strong and they are very destructive. They will create very strong and gusty winds, which are very destructive. They will cause a heavy rainfall, which is also very destructive, which will cause high levels of flooding and which will result in damage to infrastructure and will result in damage to the natural environment and also loss of lives. That is typical of tropical cyclones. So, what are the conditions which are necessary for their development? Right. We talked about Coriolis effect. Coriolis effect, we have what we call the relative deflective frequency. The deflective frequency differs according to latitude values. Deflective frequency of Coriolis is minimal around the equatorial region, which will mean that between 0 and 5 degrees out of the equator, Coriolis force is very minimal, is even or is almost 0% deflective frequency. But as we go towards the polar regions, as we move away from the equator, we increase in latitude, we increase our latitudinal values going towards 90. The deflective frequency will increase, which will mean that the Coriolis effect will become more prominent as we move away from the equator. So we are saying the tropical cyclones, for them to develop effectively, they need Coriolis force. They need a deflective effect, which is caused by the Earth's rotation. So basically, we are saying they do not occur within a region of 0 to 5 because the frequency of deflection is very minimal in that region. There is limited deflective frequency because the Coriolis force is not active in that region. It will act as we go towards the polar region. So it will mean that it will strengthen as we move away from the equator going towards the polar region. So basically, they need a region which is away of the 5 degrees north and south. They cannot occur effectively within the true equatorial region of 0 to 5 degrees. Then also they need a warm surface temperature, a warm ocean temperature. That is why the tropical cyclones, they typically happen over the Indian Ocean in the southern African subcontinent. Because the Indian Ocean, remember, it has a warm ocean and it has favorable temperatures for the development of the weather systems. So the basic temperature is 26.5 degrees Celsius. That is the minimum temperature required for the effective development of the weather system. And they also occur over tropical oceans. There's less friction. Yes, I think that's clear. They require a smooth surface where there's less friction. So basically, you must look at the factors which will favor the development of the weather system. That is basics of the tropical cyclone. Then we go to the features of the tropical cyclone. A tropical cyclone, basically, we're saying it's a low pressure weather system that typically affects in late summer to autumn. If the question asks you about the season of the occurrence of tropical cyclones, you must indicate that they occur in late summer. That is the relative response. Late summer, we're looking at months like end of February to March in the southern hemisphere. That is late summer. That is where we tend to have more of the tropical cyclones occurring because the temperatures will be relatively very high during those months. So it will favor the development and the effective formation of such typical weather system around that particular time. Right. Then also what you need to note is the tropical cyclones are named. They do have got particular names and they are named alphabetically. Alphabetically, we are talking of something which is common. The alphabet, we have the 26 letters of the alphabet starting from A until we go to Z. A, B, C, D, E. Which means in a particular season, if we have a tropical cyclone which has occurred, it is going to be given a name starting with A. Maybe it's named Alpha. That is the first cyclone of the season. If in that particular season, again, there is another tropical cyclone which has occurred in that particular same season, we name it with a letter B. Maybe we call it Beauty. And then another one in the same season, occurring again, we name it starting with the letter C. Maybe we call it Cindy. That is basically how we name the tropical cyclones. So typical questions that you are going to get in the examination, they will ask you how many tropical cyclones have occurred in that particular season. Remember, refer back to the season, to the alphabet. If you see maybe this tropical cyclone, maybe it's E. Maybe it's a tropical cyclone Elise. It means how many cyclones have occurred prior to this? There was A, there was B, there was C, there was D. This will be the fifth because alphabet E is the fifth on the list of alphabets. So you must take note of the names of the tropical cyclones because we know that they are typically named according to the alphabet. The first one to occur in a particular season is given a name starting A with A, second one with B, C, D, going until we got the last alphabet. But it's not possible even to get more than 10 tropical cyclones in a particular season. Maybe they might be maximum 6 or 7. Yes, ending there, maybe F, G. Yes, it's very rare for us to have a tropical cyclone with the letter M. That would be too much for a particular season. So that is basically what you should check for the exam as you prepare for the exams. And also, what you need to note is what typical weather conditions do they bring? They bring in heavy rainfall. They bring in strong and gust winds. And also they are rated according to categories of the destructive effect that they cause. Category 1, the weakest. Category 2, 3, going to category 5. They are also rated according to categories of the strength of the wind. Right. Let's go to particular aspects. We just want to touch on the key aspects in preparation of the examinations. We do not want to drill you through so much content or through new aspects that might confuse you as you go towards the exam. And also, if you check the tropical cyclones, they also do have particular different namings according to regions. We name them differently according to different geographical regions. Like, for example, if you check in Africa, we call them tropical cyclones. They are also called hurricanes in other regions. They are also called the typhoons. Hurricanes is typical of an American name. So if you see a weather system, maybe it's called Hurricane Florence, it's still a tropical cyclone. But why is it called a hurricane is because we are using a different naming in a particular different geographical region. Maybe it has affected places in America, they typically call them the hurricanes. If it's in Asia, they call them the typhoons. So those names, they must not also confuse you. It's different names for the same weather system according to different geographical spaces. But basically, we are looking at the same weather system. They are called typhoons in other regions, that is Asia. They are called the hurricanes, that is typical of American. We call them the tropical cyclones in Africa here. But basically, it's the same weather system. So the naming will depend with the region where the weather system has affected, because we do give them different names according to different geographical spaces. But basically, the naming will be in sequence of the alphabet. It's called Typhoon Alpha, Typhoon Beta, Typhoon whatever, according to the alphabet. But we should know the sequence that they are named alphabetically, but they are named also with different identities based on the different geographical spaces that we might be encountering them from. So for us here, we call them the tropical cyclones in Africa, and basically in Africa we use that common name. We do not infuse other names like the hurricanes or the typhoons. Then the stages of development, basically those are the stages of development. The initial development, the mature, then it actually decays. We rarely find questions on the developmental stages, but what I want to emphasize here is this section here. The section that is shaded on the part of this weather system. If you can check, there is this section here. And also if you check, there's this section here on all of the developmental stages. What do we call this section here? This is a particular section which is found on the southwestern extreme of the weather system. Why is it a specific section there? That one is called an active quadrant of the weather system. It's called an active quadrant. Active quadrant. How is it an active quadrant? That is the area where we have the most destructive winds. The winds are strongest in this particular part of the weather system. The winds are strongest in this particular section. That is why it's a unique section. It's usually secluded, it's shaded, and it shows that there is something happening there which is unique, which is not within the whole weather system. So this active quadrant, how does it come to exist? Our tropical cyclones, typically they move from the east going to the west, which means they will move in that direction. This is our west, this is our east. They will be coming from the east going to the west. And remember, we're also talking of Coriolis force. Coriolis force in the southern hemisphere, it causes winds to deflect to the left, which will mean that the winds, as they are circulating, they will also be deflecting to the left. So this active quadrant is a resultant effect of the combination of the movement of the weather system and Coriolis effect. That is why the winds are most destructive in this area here, because there is combined effect. The winds are being deflected, and also the weather system is also moving in that particular direction. And also the rotation of the weather system. Remember, it's a low pressure cell. We said rotation in a low pressure cell is clockwise. The winds are rotating in that direction, and there's deflective effect. So those effects, they will come to blend in this quadrant here, in this region. They are going in that direction because of Coriolis force. They are rotating in that direction. The system is moving in that direction. So the combined effect was going to create a very strong winds in that particular section of the system, creating what you call the active quadrant of the weather system, what you call that part. And what other question do you expect then? The other questions that you might get, you need to note the hemisphere over which the system is actually affecting. The question might ask you about the hemisphere over which the system is occurring. We said if the system is circulating clockwise, know that it's southern hemisphere. Typical cyclones in the southern hemisphere, the rotation is clockwise. But if it's anti-clockwise, you must note that it's in the north. So if you get a typical MAPWEC question or a typical practical question where you get to be asked about the hemisphere over which the cyclone is occurring, remember that whenever you see a satellite image showing clouds rotating in a clockwise direction, you know that it's in the south. If it's anti-clockwise, it means it's in the north. And also for synoptic maps, we do have different symbols which are used for the tropical cyclone. We have this symbol here, symbol like this. This is a symbol for a tropical cyclone in the southern hemisphere. It shows clockwise rotation. But if it's like this is anti-clockwise rotation. It's in the northern hemisphere. So this symbol is used for tropical cyclones. I remember this was a typical question which was asked in the term 1 test for Gauteng. They were asking about you indicating the symbol for a tropical cyclone in the southern hemisphere. Remember, the symbol is like this. It shows that the system is rotating in that direction. If it's like this. If it's like this is rotating in that direction, which means it's anti-clockwise, it's in the north. Always remember that it's clockwise in the southern hemisphere. So the system is shown by the rotor like this. Then if it's anti-clockwise, it is shown the other way around. This is clockwise, this is anti-clockwise. So also take note of those ones. If the question asks you about the hemisphere over which the system is affecting, please be mindful of how the symbols are different between the northern hemisphere tropical cyclone and the southern hemisphere tropical cyclone. Right, let's quickly go through the tropical cyclones. If you get a question asking about the impacts of tropical cyclone, maybe the question is saying discuss the impacts. Impacts, if it's not specific, positive or negative, it means you have to account for the positives and for the negatives. If it's just saying impacts on the environment, it means positive benefits of the system over the environment or negative benefits. And then what you need to note is when you are asked as referring to that particular question, you should note the aspect of the weather conditions which are brought by the system. Talk about destructive effects which are caused by strong winds, or talk about effects which are caused by heavy rainfall. Because typically we know that tropical cyclone, they bring with them very heavy rainfall, which is going to cause flooding and which is going to cause destruction of infrastructure, loss of lives, loss of air. That is typical weather condition. And also they're going to cause very strong and gusty winds, which are going to cause also destruction. So when you're addressing the question, take note of the aspects of the weather conditions which are going to be brought by the coming of the weather system. Then you can figure out how to answer the question. So basically, this is typical of an indication of the weather system on a satellite image or on the synoptic map. Right, we move on. The cross section is like that. This is the eye of the system where there's descending air and where there are clear conditions at the middle of the weather system. And there's strong ascendance by the side of the system. We have the eye wall and we have the vortex developing here where we have vertical upliftment of the air. And we have typical of cumulonimbus clouds forming, which are tall and towering clouds created by the vertical ascent of the air as it circulates around the eye of the weather system. Right. Let's move on to the next aspect. This is tropical cyclones. This is typical second aspect of the. We're looking at traveling disturbances. Traveling disturbances associated with winter conditions and with summer conditions. Right. What you call the traveling disturbances, we are looking at typical weather systems that result as that are caused by the existing pressure cells over the subtropical high region. South Africa, we say it is lying within the subtropical predominantly, and that is going to cause different weather conditions over the subcontinent of Southern Africa. We have the high pressure cell, the South Atlantic, we've talked about them. South Atlantic on the west, the Kalahari high pressure cell, and the South Indian are on the east. They do have an impact on the conditions which are going to be experienced over the interior, and they do affect the weather systems. That is what we call the traveling disturbances, which are typical of the subtropical and the cyclonic weather systems. Traveling disturbances in the sense that these pressure cells, what you should also note is they are not situated permanently on the same geographical space. They do have movements that they do. They move latitudinally with the shift of the ITCZ. That is the South Atlantic high pressure to the west and the South Indian high pressure to the east. When the ITCZ is further to the north, meaning to say is typical of southern hemisphere summer, the pressure cells will also latitudinally shift going towards the north. They will move latitudinally like that. And when it's winter, when it's typical of winter in southern hemisphere, they will be further to the north. Then when it's summer, it means the ITCZ is south of the equator, and they will also drift further south, so that they move latitudinally according to the shift of the ITCZ. So they are not stationary, they do move to the north and to the south according to the differences in the shift of the ITCZ, giving us differences in the seasons. Right. So in the Kalahari high pressure, so these are the two, the South Indian and the South Atlantic are the ones that move latitudinally. But the Kalahari high pressure cell does not have the same behavior. This one, we call it a vertical displacement. It's displaced vertically. It has what we call a vertical displacement, meaning to say the high pressure cell is dominant when there's strong descending air. That is typical of winter conditions. When we have typical winter conditions, we have stable conditions over the interior. We do not have precipitation. We do not have cloud formation because there will be typical descending air. But however, it becomes weaker over summer, meaning to say the high pressure cell is now elevated, is vertically displaced, is now in the upper atmosphere, is now weaker. The descending air is no longer reaching the surface. That is how the Kalahari high pressure cell moves. It is vertically displaced. These ones are latitudinally displaced. The South Indian and the South Atlantic, they displace latitudinally according to the shift of the ITCZ. They move further to the north when it's winter in the southern hemisphere because ITCZ will be in the north. Then when it's summer, the ITCZ is to the south of the equator. They will also drift southwards because of the shift of the ITCZ. But the Kalahari high pressure cell is vertically displaced. It's stronger during the winter season. There is strong descending air over the interior in winter, but however, the high pressure cell, it weakens over the summer season. So we want to look at how do they affect the weather systems over the interior of South Africa, and how do they also affect the weather conditions over the coastal regions. Quickly, typical questions that you can get. You get a question on line thunderstorms or a question on the moisture front. It's typically one thing, the moisture front and line thunderstorms. All right, let's go directly to the moisture front and line thunderstorms. All right, before we look at that even, let's look at the impact of the Kalahari high pressure cell. We said it's stronger during winter. When you get a question which asks you about the position of the inversion layer, right, what you should note there, do not use queer terms. Refer to the inversion layer as being above the escarpment or being below the escarpment. An inversion layer, we are saying, this is a layer of warm air which is trapped. Or basically, before we do look at the inversion, let's look at the concept of the inversion. The inversion is basically the reversal of the normal temperature profile of um the normal temperature profile within um the region of our the workings of the normal temperature profile. Right. We are saying we expect temperatures to be lower in the upper atmosphere. We are saying the higher you go, the cooler must it become, because the source of heat is the Earth's surface. The Earth's surface receives insolation, and it is going to cause radiation. And the more we are close to the Earth's surface, it means the temperatures are higher in the troposphere, close to the ground surface. But as we go up in the atmosphere, the temperatures must decrease. So what you call a temperature inversion, usually you get that question. The temperature inversion is the reversal now. We are going up with altitude, but the temperatures are increasing. Whenever we have a situation whereby temperatures are increasing with altitude, that is an inversion. So when you get a typical question asking about the inversion, always remember that it's a reversal of the normal temperature profile of the troposphere. We expect temperatures to drop with altitude or with height, but when we have temperatures increasing with altitude, that is now an inversion. It's not longer normal. The temperature profile must be negative. Temperatures must drop as we go into the upper atmosphere because we are moving away from the source of heat. But an inversion now, if the temperature increases with altitude, it means that is particular of a temperature inversion. So we have this inversion layer here. It's a belt of warm air which is trapped in between two cold air masses. And this inversion layer here, it is going to change its position in summer and in winter because of the effect of the Kalahari high pressure cell. Remember, we said the Kalahari high pressure cell is vertically displaced, which means it's weaker during the summer season. And if it's weaker, it means it's elevated. It's in the upper atmosphere. And this layer here is going to be also elevated. If you check the terrain here, this is our sea, and we have air which is supposed to feed over the interior here, coming from the Indian Ocean. This air will bring in moist conditions over the interior, and because there is a passage gap here, the inversion layer is elevated, is not blocking the coming of the warm and moist air over from the Indian Ocean. The air is going to reach the escarpment, is going to get over the interior, and it's going to reach dew point, condense, and form clouds. That is why we have typical wet conditions over the interior in summer, because there is weaker descending air. The Kalahari high pressure cell is elevated, is weaker, is vertically displaced, and is not forcing the inversion layer over the plateau. The inversion layer is well above the plateau. So you get typical questions there, which will ask you about which season is indicated. If you see a scenario like this, the inversion layer is above the escarpment, typical of summer conditions, which is going to bring wet conditions over the interior. The warm and moist air is going to feed into the interior and create wet conditions. That is typical of summer conditions. Right. Then we go to winter conditions. You see now the inversion layer is lower, is below. When you get a question or when you get a question requiring you to describe the inversion layer, use the term the inversion layer is below the escarpment. It's below, the escarpment is here, and the inversion layer is here. Meaning to say, the inversion layer now has been forced to go down by the strong descending air of the Kalahari high pressure cell. It's stronger. This is typical of winter conditions. When it's winter, we have strong descending air, and the air which is descending is going to force the inversion layer to lower below the escarpment and block incoming warm and moist air here. That is why we have dry conditions, because the air which is supposed to feed moisture over the interior is being blocked by the inversion layer. So typical questions, they will ask you about the season. What you should not check the position of the inversion layer. If it's elevated, it's above the escarpment, it's typical of summer conditions. And what kind of weather conditions do we experience over the interior? We have moist conditions, we have rainfall, we have unstable conditions. And when it's like this one, the inversion layer is lower, is below the escarpment, it will create dry conditions and stable conditions over the interior. Warm and moist air is blocked from reaching the interior. That is typical of questions that you get on traveling disturbances associated with summer and winter conditions. Right. Let's move on to the line thunderstorms and the moisture front. Line thunderstorms, we have the South Atlantic here, we just summarize, and the South Indian. These two high pressure cells are going to feed in air into the interior. Because of anticyclonic circulation, we do have air which is being fed from the South Atlantic and air which is being also fed into the interior from the South Indian high pressure cell. And these ones are typical traveling disturbances that occur over the summer season. When we do have summer conditions, we have high amounts of rainfall occurring over the interior because of the implications which come from the South Atlantic high and the South Indian anticyclone. They feed in air over the interior, but the air that they feed over the interior will be different. Remember, over the Atlantic Ocean, we have cold conditions. It's a cold ocean, and it is going to bring in cold and dry air over the interior here, like what you are seeing. We're going to have cold and dry air being fed anticyclonically in an anti-clockwise direction. And also from here, the South Indian, because it's a warm ocean, there's a warm ocean current, is going to feed a warm and moist air. And those two air masses, remember we talked about the differences in the properties of air masses. Whenever we have two air masses of different properties, those two air masses are different in terms of their temperature and their moisture content. One is cold, the other one is warm. That is temperature. The other one is having moisture, the other one is dry. So they cannot mix. They are going to be split by a front, which is the boundary here. So this boundary is the one that we call the moisture front. Moisture front in the sense that it's going to create wet conditions. How are the wet conditions going to be realized? This air here is cold and is denser. This air here is warm and is less dense. When the two air masses meet, the cold air is going to subside and is going to force the warm air to rise. As this air rises, it reaches dew point, it creates clouds that will form rainfall. And the rainfall is going to occur in a line because the boundary will be more of a linear across South Africa. And the system moves from the west going to the east, which means the rainfall is going to be realized as the system is also going to move in that particular direction. And we have rainfall being experienced on the eastern part of the front because that is where the warm and moist air is coming from. So typical questions that you can get there, you need to note where we have high rainfall. We have high rainfall on the east because that is where warm and moist air is being fed from. It's coming from the South Indian anticyclone. And on the left side, on the western side, there is cold and dry air, which means, and also the system will be moving in air in an easterly direction. It will be moving from the west going to the east because the cold air will be pushing towards the direction of warm air, which is coming from the east. And also what you should note there, you must also note the fact that there will be line thunderstorms. Line thunderstorms are saying there will be a series of thunderstorms occurring along the moisture front. Like usually it's indicated on the synoptic map, like you will see, there will be symbols like this, and they will be in a line, indicating that we have typical thunderstorms occurring in a line. That is what we call the line thunderstorms. They will be occurring along the front. They will be occurring in a line along the front. So basically, that is what we call the traveling disturbances, which are caused by the subtropical anticyclones and typical of summer disturbances. Then we also have winter conditions over the coast, what we call the backwinds. The backwinds, basically, they are caused by the descending air, which is coming from the interior, going down to the coast here, like what you are seeing. We have the strong descending air over the interior because of the Kalahari high pressure cell. The air is going to hit adiabatically and it's going to get very high temperatures as it gets to the coast, which is typical of the Berg winds, and they are going to cause hot conditions and uncomfortable conditions for people over the coastal regions because of adiabatic heating. And also what you should note is preventive measures for the berg winds. How can people prepare for them? You look at things like controlling the wildfires. There's high chance of wildfires occurring, or keeping the ground wet to avoid the spread of wildfires, or people keeping water resources to avoid dehydration, or that is basically the berg winds. I think the information is there. And then we also have typical of the coastal low pressure cells. We have the low pressure cells occurring along the coast. They move from the west going to the east along the coastal region. That is typical of the coastal low pressure cells. Right. Then we need to move on to valley climates. On valley climates, we want to focus on slope aspect, and we want to focus on the anabatic and the katabatic winds. Right. What you should note with these ones, we just want to summarize them as quick as is possible. Right. We do have what we call slope aspect. What is it that we call a slope aspect? When we're talking of slope aspect, we are looking at the orientation of the slope. We are looking at slope aspect. We are looking at orientation of the slope. What is orientation? Where is the slope facing? Right. We know well that when you're looking at slope aspect in the southern hemisphere, we have our overhead sun's position always in the north, because the sun deviates within the equatorial region, within the tropical region, 23.5 north and 23.5 south, which means here in southern hemisphere, if we have a slope which is facing towards the north, that slope is going to receive insolation during winter, and the other slope facing the opposite direction is not going to receive any insolation. That is slope aspect. We are looking at the orientation of the slope. Where is the slope facing? So in the southern hemisphere, we are saying the north facing slopes, they are the ones that receive insolation in summer. Like, let me indicate, if this is our south day and this is our north, we are saying the sun is in the north. We are in the south here. The sun is always there. And it means the sun is going to shine over this. And it will never shine over this, because this one is facing away from the sun, but this one is facing towards the sun. This is what you call, what you call the zone of incidence. Zone of incidence. And this is what we call the shadow zone. So we are saying the shadow zone is always in shadow, does not receive insolation because it's facing away from the sun. And the zone of incidence is the one which is receiving insolation, is facing towards the direction of the sun. So typically we have effects on this side and also effects on the other side. Like on settlement, you tend to find that people prefer to settle on the warmer part of the slope. And also on agriculture, we have typical agricultural activities which favor the either side of the slopes. Like, for example, the shadow zone, we have activities like the farming of the plantations, because they favor relatively cool conditions and also moist conditions. And also on the side, we have agricultural activities of crops that require relatively higher temperatures. So it will affect activities happening and also to affect the nature of the settlement on either side of the slope. Right, let's go to we want to focus mainly on katabatic and anabatic winds. Those are the typical questions that you can get. Right, I'll explain quickly on the anabatic and katabatic winds. Right, if we have a valley, we do have typical winds that are going to be experienced in that particular valley condition. Right, what is going to happen here? Let me illustrate. Right, because of this situation, if we are having a valley like this, it means this is the floor of the valley and these are the valley sides. Let's say we are in the southern hemisphere, our sun is there in the north, which will also mean that the sun's rays are going to, in winter, because the sun is lower in the atmosphere, are going to only affect this. Because of slope aspect, this is what we call the north facing slope. And this is the south facing slope. So the north facing slope in the southern hemisphere is the one that receives insolation. This one here is the one which is heated directly by the sun. But this one here is in the shadow zone, is facing away from the sun. So what is going to happen here is, because of this implication of the sun's rays, which are going to hit this side, they are going to create pressure gradient. There is insolation during the day, which will mean that there will be higher temperatures. The surface is going to be heated. And remember the relationship between temperature and pressure. Whenever we have high temperature, the pressure is going to be low. So because of high temperatures caused by insolation, the pressure is going to be low pressure. And as a result, the valley floor now has got higher pressure compared to the valley side. And there's now pressure gradient. There's now high pressure in the valley floor and there's low pressure on the valley side. It's going to cause the air to blow in that direction. It's going to go up. From the floor of the valley, it's going to go up because there's low pressure there. This is typical of what we call the anabatic winds during the day, and they are typical day winds. So typical questions that you can get a question which will ask you to mention or to name the type of wind in the valley. Whenever you see an upward movement of a wind from the valley floor going to the valley side, that is typical of anabatic, and that happens during the day. Then what happens during the night? There is reversal of the movement. During the night, the valley side now becomes cold. How does it get cold? It gets cold because of long wave radiation, or what we call terrestrial radiation. There is loss of heat from the valley side during the night because of long wave radiation, and the valley side now becomes very cold compared to the valley floor. The valley floor would now be relatively warmer compared to the valley side. And now that is going to cause a low pressure developing here and a high pressure developing on the valley side. And the wind is going to reverse. It's going to go to the bottom of the valley floor. This is what we call the katabatic, which is a downslope wind. So if you get a question which asks you about mentioning the wind, remember that whenever we have a downward movement of the wind in a valley, that is typical of a katabatic, and it happens during the night. Then we also have other aspects which are very important that we must note. We need to talk about the inversion layer. We talked about that. We all look at the inversion layer in the valley. Right, the inversion layer, we're saying if there's a valley like this, and if there are katabatic winds going down, these winds are cold. They are going to displace the warm air which was in the valley, and the warm air is going to uplift. But however, the warm air is not going to be able to escape the valley because this is winter. There is strong descending air also. The Kalahari high pressure cell is causing a strong descendance, which is going now to block this air. So the air will end up in the valley, not out of the valley, but being trapped between two air masses of cold air, which is descending, and also cold air, which was katabatic, which was sinking into the valley. This is what we call the thermal belt. It's called the thermal belt. Is a band of warm air which is trapped between two cold air masses. There's cold air from the top and there's cold air from the bottom, and this warm air is trapped in between, creating a thermal belt. So typical of the valley climate, we also have thermal belts forming, and they also influence settlement. People usually want to settle along the thermal belt here because it's relatively warmer. Right, let's quickly go on. That is with the valley climate. So we also have frost pockets. Frost pockets, they form here. How do frost pockets form? Frost pockets form when dew point is below freezing point, when condensation level is below freezing point. If the air which is coming here is having moisture, and is going below the freezing point, is going to cause accumulation of frost or ice in the valley. That is typical of frost pockets. So it's typical of a question that you can also get on valley climates. So basically, you need to know the katabatic and the anabatic winds. You need to note the thermal belt. You need to note the influence of the valleys on settlement and on activities happening on settlement and of agriculture, and also the implications of frost pockets. It will also affect agricultural activities. Farmers have to grow crops which are frost tolerant if they are in a valley condition. And also the thermal belt, remember, it also affects the levels of concentrations of pollutants in the valley. Like we do have a formation of foggy conditions in the valley because of the trapping of pollutants, which will give hygroscopic nuclei of condensation in the valley during the winter season. That is why you tend to find that usually in winter, in areas which are typically valley, we do have foggy conditions, which will reduce visibility and usually will cause traffic problems because of poor visibility. It's because of the pollutants which are trapped by the inversion layer. They cannot escape the valley and they will give condensation nuclei, which is going to cause misty and foggy conditions, which will reduce visibility and cause very serious traffic incidences. Right. Then with that, I think we are done with the valley climates. We need now to conclude by looking at the urban climates. The urban climates, basically, we are looking at urban areas. How do they affect? How is the climate of an urban area different from the climate of a rural area? I will touch on two aspects here. I will touch on an urban heat island, and I will also touch on a pollution dome. I think those are the two basics of urban climates. Then I think that will be fine for urban climates. Right. What we need to note here, there are two instances of urban climates. The urban climatic conditions are different from the rural climatic conditions in two dimensions, one in terms of temperature and also in terms of the level of pollutants. Right. We have what we call an urban heat island. Urban heat island. When you get a question on an urban heat island, your focus must come here to the heat part. What is heat? We're talking of temperature. And what about the temperature? We are looking at an urban area which has got a high temperature compared to the surrounding rural areas. You are done with an urban heat island. The moment you figure out that when we're talking about an urban heat island, we are worried about the temperature of an urban area being higher than that of a rural area, that is done. What causes the urban area to have high temperatures? Now you talk of the factors which promote higher temperatures in an urban area. For example, built up surfaces, for example, concrete surfaces. You talk of reflection from the buildings. You talk of the number of buildings. You talk of pollution in the urban area. You talk of but there are a lot of things which will contribute towards the urban areas having higher temperatures compared to the rural areas. That is an urban heat island. And also the implication of the heat island, how does it affect human activities? Causes dehydration, causes activities like fatigue, causes whatever is within the line of high temperatures in the urban area. That is typical of an urban heat island. How can we reduce the impact? How can we reduce urban heat islands? You now look at maybe introducing natural surfaces, introducing water bodies in the urban area, like you talk of the recreational parks in the urban area. Introducing vegetation in the urban area is going to lessen the impact of the urban heat island. That is the basics of the urban heat island. Then we go to a pollution dome. A pollution dome, we are looking at the concentration of pollutants in an urban area. Pollutants, we're looking at maybe smoke from the vehicles, smoke from industries. We're looking at those pollutants. They do concentrate in the urban area and they are going to create hazardous conditions to the urban dwellers, what you call a pollution dome. And what I want to focus on here over the pollution domes, we have two situations that you might get, maybe if you get a typical question in the examination. We have the day conditions of a pollution dome, and we have the night conditions of a pollution dome. During the day, the pollution dome takes this shape. This is our urban area, the buildings are there, and during the day, the pollution dome is elevated. The concentration of pollutants is limited. The pollutants are displaced vertically in the atmosphere. Why? Because we are having a surrounding rural area which has got cooler temperatures, and which will mean that there will be higher pressure to the outskirts of the urban area. And because of intense heating in the urban area and because of the urban heat island, is going to cause a low pressure inside the CBD. And the air is going to blow, feeding into the built up area. And there's convergence, the air is going to uplift and will diverge in the upper atmosphere. As the air is uplifting, is also displacing the pollutants. So the effect of the pollution dome is less during the day because the pollutants are displaced vertically into the atmosphere, they are plummeted and they are not concentrated. But however, at night, the effect is now felt. Like the pollution dome is now taking that shape. The buildings are there. And now, because of strong descending air, pollution domes are also typical of winter conditions because there's strong descending air during the night, and the low pressure now is no longer existent because there is no more insolation in the urban area. The level of pollutants is now concentrated here. Like the pollutants are now being forced to lower their level because of the strong descending air of the Kalahari high pressure cell, and we end up having a situation of high concentration of pollutants close to the ground surface because of the strong descending air. So the pollution dome during the day and during the night, that is typical of the night condition and typical of the day condition. So during the day, the pollution dome is elevated, is high up in the atmosphere. The pollutants are vertically displaced, they are not concentrated, but during the night, because of the impact of the strong descending air, they are now concentrated and they are now affecting human activities in the urban area. That is basically what you should note. So as we are preparing for the examinations, I urge you to be diligent, and the advice is you must attempt all the questions. Do not leave blank spaces. Attempt all questions in as much as you understand, answer the question. And also remember, if you're answering paragraph questions, follow the instruction, give the responses in paragraph format, giving a factor and also qualifying your factor. We are expecting that with geography as a subject on its own, failures must be very minimal, or we might not even talk of anyone failing to get a level 4, a level 5, because these things are practical, these things are just realistic, these things are just within our reach. We are experiencing them. Like if you talk of climate and weather, starting from the tropical cyclones, we talk to mid-latitude cyclones, they are actually practical, it's a living subject. So in as much as you understand the geographical aspect of what happens in your day-to-day life, apply them in the examination, and it must be 100% pass for geography across the whole of South Africa. And it has been like that, or it must maintain that standard. So we hope that you this discussion is going to actually benefit you in some dimension, and is also going to assist you in whatever you will encounter in the examination. And the other thing is confidence. Be very confident of yourself. When you get to maple calculations, can you please be very accurate with your calculations? Try to be accurate with your measurements. Try to be accurate with your calculations. When it's a payment of bearing, can you please use your protractor precisely and get the correct bearing, get the correct measurement, get the correct calculation, and everything must be in position. It is my belief that 2024 is your year. In geography, I believe everyone must be attaining 100% pass as a subject, and also as an individual, I urge you to attain the best of your level. The world has more to offer that is waiting for you. I thank you for being with the discussion. Your host, Conrad Mpinguren. Thank you.